All right, let's go ahead and find the IOC for this series, the interval of convergence. We are going to attack it with the ratio test. So we will take the limit as k goes to infinity of the absolute value of the ratio of consecutive terms. So we'll put a sub k plus 1 in the numerator, a sub k in the denominator, and take the limit. So a sub k plus 1, we are going to replace all the k's with k plus 1. So that's going to be 2 times the quantity, k plus 1, plus 1. That's the numerator, and we want to be an absolute value. The denominator is always positive, so we don't need to deal with absolute values there. So there's a sub k plus 1 in absolute value. Dividing by a sub k means multiplying by the reciprocal. Oops, I did one thing wrong over here. This k was supposed to be replaced with k plus 1. So it's k plus 1 minus 1. There we go. And then flipping a sub k, putting absolute values on the part that have an x in them. So it looks like this. Now we need to go ahead and simplify. Let's first do some simplification in these exponents. And then we'll do some more simplification. So that's going to be 2k plus 2. And if we add 1 to that, we get 2k plus 3. And then down here, we'll have 5 to the k. This numerator, this exponent can't simplify at all, nor can this exponent. So we're good to go now. Let's first take a look at the powers of 5. We have 1 extra 5 in the denominator. I'm going to write my fraction bar. I'm going to put 1 5 down there. All right, there's 1 fewer 5 in the numerator, k minus 1. Now with the x's, my fraction bar is looking very big there. With the x's, we have powers of x in both numerator and denominator. So the law of exponents says we are going to subtract the exponents. So 2k plus 3 minus the denominator's exponent. And when we subtract off that denominator's exponent, we have to distribute that minus sign. And there we go. All right, so let's keep on simplifying. That exponent on the x then becomes 2k minus 2k. Okay, those cancel, right? And this 2k minus 2k. And then we have 3 minus 1, which is 2. So we have x squared over 5. And then we realize that, gosh, x squared is always positive, or at least non-negative. So we don't really need those absolute value bars after all. And now, this limit is based on k. It says k goes to infinity. Do we see a k in that expression? No, we don't. So that expression is constant with respect to k. So that means that the limit is itself. When we have the ratio or the root test, once we complete our limit, we want to know the values of x for which this is less than 1. Less than 1 is going to give us absolute convergence. So we want to know which x's give us absolute convergence. So let's go ahead and multiply both sides by 5. So we have x squared less than 5. And this is going to lead us to the structure of our interval. So x squared less than 5 means that x is going to be trapped between the square root of 5 and the negative square root of 5. X has to be in between. So this is not our interval of convergence yet. Okay? The interval of convergence will have endpoints of negative root 5 and root 5. So we could come down here and foreshadow a little bit. The left endpoint will be minus root 5. The right endpoint will be root 5, but we don't know whether we include or exclude the endpoints yet. So at this stage, all we can do is conclude that the radius of convergence is square root of 5. Let me point out also that this power series has a center of 0. We don't have a displacement on x. We have just x. We don't have x minus 5 or x plus 2 or something. So the center is 0, and that's reflected in the radius of convergence here. This is symmetric around x equals 0, and the radius of convergence is the distance from the center over to one of these endpoints. So the radius of convergence is root 5. So the next stage of this is to figure out what happens at the endpoints. So let's go ahead and take the left endpoint, x equals minus square root of 5, and we want to determine whether we have convergence or divergence at that endpoint. So we are going to go back to the original series and plug in for x negative square root of 5. So we have negative root 5 raised to the 2k plus 1, all divided by 5 to the k minus 1. So we want to analyze this endpoint now. All right, let's go ahead and simplify that numerator. So we're going to take that numerator, and I'm going to partition the base. So I'm going to make this negative 1 to the 2k plus 1, and then square root of 5 to the 2k plus 1. And then we have the denominator as is. When we look at this exponent on the negative 1, 2k is always even. And if we add 1 to an even number, we get an odd number. So in this expression, we have negative 1 raised to an odd power, which is going to simplify to just negative 1. So we have negative 1. I'll put it in parentheses for now. Now this power of 5 here, we have a 5 to the half inside here. Down here we just have a 5, so we'd like to try to match these. So I'm going to rewrite that as 5 to the 1/2. And when we have a power raised to a power, we are going to multiply the exponents. And then in the denominator, we still just have this 5 to the k minus 1. All right, we're getting somewhere very slowly. The minus 1 here, I can factor that to the front. Constants can factor out. And a constant multiplier does not affect convergence or divergence. So let's see, what do we have in here? We distribute that half, and we're going to have k plus 1/2. And down here we have 5 to the k minus 1. So now we have powers of 5, and we can simplify this. Excuse me. So this is going to be the numerator's exponent minus the denominator's exponent. So we're going to have 5 raised to the k plus 1/2. And then we're going to subtract off the denominator's exponent. And when we subtract off that denominator's exponent, we are going to have the following. And I'm thinking I'm going to move this over here so that we have a little bit more space. So let's do this. All right, so it's k plus 1/2, and we are subtracting off the denominator's exponent. When we subtract it off, we need to distribute that minus sign. And we are going to be left with 5 to the, okay, these two cancel. And we're going to have 1/2 plus 1, which is 3/2. Now, this series is going to be divergent. Let me make sure it's clear why. This is a constant, so it could factor to the front. And when we factor that constant out, we're left with a 1. And it needs to be clear that this series right here, that series, means that we're going to be adding 1 to itself an infinite number of times. So that is divergent. So if we add 1 to itself an infinite number of times right there, that's what that series represents, 1 plus 1 plus 1 plus 1, this series diverges. Now, the reason it diverges is because this is a sub k, and the limit of a sub k is not equal to 0. So that's why we get divergence here. Okay, because the a sub k is not going to 0. So that tells us that we are going to exclude the left endpoint in our interval of convergence. Now, let's jump to the right endpoint. So the right endpoint, we're going to let x equal positive square root of 5. And we're going to substitute that into the series. And when we plug it into the series, we are going to have the square root of 5. That's all going to be raised to the exponent of 2k plus 1. And the denominator is 5 to the k minus 1. So now let's analyze the convergence or divergence of this. So once again, in the numerator, we are going to deal with this square root of 5. We're going to turn that into 5 to the half. So that's going to be 5 to the half. And that's going to be multiplied by this other exponent. Power to power you multiply. So 2k times 1/2 is going to be k. 1 times 1/2 is 1/2. So there's the numerator. Here's the denominator. And once again, we are going to subtract numerator exponent minus denominator exponent. So k minus k is going to be 0. And then we have 1/2 minus 1, so that's 1/2 plus 1, which is 3/2. And once again, we have a series that will diverge. Now you have a couple of ways to analyze this here. If you want to analyze it in this form right here, it's totally fine. You could think of this as 5 to the 3/2 added to itself an infinite number of times, which will be infinity, and so we'll get divergence. Or you could factor it out to its simplest form, where we have a 1 on the inside, and just like above, that means 1 plus 1 plus 1 plus 1 forever and ever. And our justification is that the limit of a sub k, it's not 0. The limit of a sub k is 1, right? The limit of a constant is itself. And if that's not 0, our conclusion is diverge. So now we have divergent endpoints. So this power series diverges at both endpoints. Now we can conclude that our interval of convergence doesn't include either endpoint, and it goes from negative root 5 to root 5. And the radius of convergence is square root of 5.